Welcome to The Explainer. Imagine, if you will, a sweeping view of a complex, futuristic city. Everything is perfectly interconnected, humming with invisible energy. Well, that's exactly what the complex data ecosystems of modern applications look like today. We're diving into Chapter 12 of Martin Kleppmann's acclaimed work, looking at the future of data systems. We've totally reached the limits of the old one-size-fits-all database, and today we're exploring how the future relies on seamlessly integrating diverse, specialized tools, making sure they actually work when things inevitably break, and grappling with the profound moral responsibility we take on when we build them. Let's get into it.
To kick things off, think about this incredible quote from computer science pioneer Alan Kay. He noted that the internet was done so well, most people literally think of it as a natural resource, like the Pacific Ocean, rather than something man-made. It's a brilliant way to frame our discussion. When we build truly exceptional data systems, they just kind of fade into the background, right? They become this invisible, hyper-reliable infrastructure powering our daily lives. But as we all know, getting to that absolute peak level of scale and reliability, yeah, it's incredibly complex.
Section 1. Beyond one-size-fits-all. Reaching the limits of the monolithic database.
Okay, let's dive right into this. For the longest time, the default approach in software engineering was simply to rely on a single, massive, monolithic database to handle literally everything an application needed. But folks, that era is officially dead. Modern data ecosystems are just way too complex now. Sure, a traditional relational database is fantastic for processing transactions, but is it optimized for full-text keyword searches, or complex machine learning models, or sub-millisecond caching? No, absolutely not. To pull all of that off, we're now forced to stitch together highly specialized tools. We're talking caches like Redis, message queues like Kafka, and search indexes like Elasticsearch. We are essentially living in the age of polyglot persistence, combining all these different tools simply because no single piece of software can do it all efficiently anymore.
Section 2. The database inside out. Unbundling storage and data flow.
So, if we can't use one database for everything, what's the fix? Well, the really fascinating solution is to take the database and literally turn it inside out. We need to take those internal database mechanisms and apply them across our entire architecture. We're looking at a stark contrast here between the old and the new. In the traditional setup, you have the past, monolithic, highly reliant on synchronous ACID transactions to keep everything perfectly consistent inside one rigid box. But the future? The future is unbundled data flow. It's event-driven, and crucially, it's asynchronous. Instead of forcing every single thing into a monolith, we just let the data flow naturally between specialized components that are actually optimized for their specific tasks.
Now, a real game changer making this whole thing possible is Change Data Capture, or CDC. CDC is basically the process of observing all the data changes being written to a database and extracting them as a continuous stream. Back in the day, database replication logs were these hidden, highly internal details, but CDC frees that information. It allows us to tap directly into that log and replicate state changes instantly across entirely different technologies. That means we can keep our search indexes and our caches automatically synced up with our primary database without breaking a sweat.
Let's walk through exactly how this builds into a complete asynchronous pipeline. Step 1 is our event log. This acts as the absolute authoritative system of record. Then, step 2 is the stream or batch processor that reads those events and transforms them. Finally, step 3 is the derived data system, so things like a search index or a materialized view. And that is what the end user is actually querying. We are quite literally translating write-optimized event logs into read-optimized application states. It's a beautiful flow.
And here is why this matters so much. In this unbundled architecture, that append-only event log acts as the central nervous system. By treating every single change as an immutable event in a log, we totally bypass the need for those heavy, incredibly fragile distributed transactions. You know, things like two-phase commit, which honestly often amplify failures, because if just one system slows down, the whole thing grinds to a halt. The event log completely decouples our systems. It allows one consumer to temporarily fail or just slow down a bit without taking the entire architecture down with it.
Section 3. Aiming for correctness. The harsh reality of software and hardware failures.
Okay, so it's not all smooth sailing. Out here in the chaotic real world where hardware fails, networks drop packets, and software just bugs out, how do we actually ensure correctness when data is flying asynchronously across a dozen different systems? Well, the very first principle we have to wrap our heads around is the end-to-end argument. This principle basically states that databases alone cannot magically save us from data loss. Think about it like TCP on a network. TCP ensures your packets arrive in order, sure, but if a user furiously clicks a checkout button twice because their UI froze up, TCP can't stop that duplicate order. The application itself absolutely must take responsibility for end-to-end correctness, typically by passing a unique request ID all the way through the pipeline.
And that unique request ID, that brings us to our primary technical shield, impotence. An impotent operation is simply one that you can perform multiple times, but it has the exact same effect as if you only did it once. For example, setting a specific value to a variable is impotent. Just incrementing a counter, not impotent. By making sure our stream processors and database writes are impotent, we can safely retry failed operations over and over without wreaking havoc on our data. It completely sidesteps the need for massive, complex distributed locks.
Now, what's really interesting here is how we often incorrectly lump two very distinct concepts together under the broad umbrella of consistency. First up, we have timeliness, which is just the delay before you actually see your data. Violations here are temporary, eventual consistency kicks in, and it's resolved just by waiting. It's a minor annoyance at worst. But then we have integrity, the absolute absence of data corruption. If integrity is violated, the data is permanently contradictory, and the consequences there, they can be catastrophic. Think money just inexplicably vanishing from a bank account.
So the crucial takeaway is that because integrity is so absolutely paramount, we have to abandon our blind trust in underlying technologies. Hardware lies to us, disks silently corrupt data all the time, and software always has bugs. We really need to embrace a culture of continuous verification, a true trust but verify philosophy. We just cannot assume that because a database promises ACID transactions, our data is magically safe from our own application-level bugs.
To actually put trust but verify into practice, the systems of the future are going to need to continually prove their own integrity. We're going to see way more self-auditing systems that run background checks, kind of like how massive storage systems like HDFS continually scrub their disks to find silent corruption. We'll use explicit data flow provenance to trace any piece of derived data right back to its source event. And honestly, we'll probably increasingly rely on cryptographic integrity checking and Merkle trees, the exact same tech powering distributed ledgers, to mathematically validate that our data hasn't been quietly messed with.
Section 4. The ethics of data. The moral responsibilities of software engineers. Let's shift gears a bit, because building scalable, reliable systems isn't just a fun engineering puzzle, it fundamentally impacts real human lives. The sources we're looking at strongly warn about the dark side of predictive analytics and massive data collection. When poorly considered, these systems can amplify existing human biases and create incredibly destructive feedback loops. Situations where algorithms predict an outcome, influence reality to make it happen, and then use that new reality as proof they were right all along. It's a cycle that can literally lock individuals into algorithmic prisons, making life-altering decisions about things like credit, housing, or criminal justice completely without transparency or consent, all while normalizing a deeply concerning culture of mass surveillance.
The author, Martin Kleppmann, leaves us with a really powerful dedication in his book. He writes, "Data, software, and communication can be used for bad, but they can also be used for good. This book is dedicated to everyone working toward the good." It's such a vital reminder. The technical creations we pour our time into ultimately dictate human lives. The algorithms and event streams we design, they do not exist in a vacuum.
We always have to remember that the ultimate goal of data systems isn't just achieving some massive, mind-boggling scale, or processing millions of messages a second, or hunting for the lowest possible latency. It's about building maintainable, reliable infrastructure that respects human rights. Scalability has to include humanity, dignity, and respect. Because frankly, if a system harms people, it really doesn't matter how technically elegant or perfectly unbundled its architecture is.
So as you go out there and engineer the interconnected digital cities of the future, there is one final, provocative question I want to leave you with. How will you build data systems that don't just process millions of requests, but actually treat users with humanity? Keep that question at the absolute forefront of your mind. Thank you so much for joining me on this Deep Dive Explainer, and as always, keep learning.